Hello, my name is Tatiana Marugo, and in this video, I will support exercises 1, dual analysis, 2, sensitivity analysis, and 3, post-optimal analysis, which I conducted on a linear programming model applied to alloy steel production. This model aims to maximize profits subject to resource usage constraints such as steel, heat treatment time, and other inputs. Ejercicio 1, Análisis Dual, Exercise 1, Dual Analysis. In this first exercise, we start from the primal model that minimizes the production costs of 3 types of alloy steel, Type 1, Type 2, and Type 3, subject to usage constraints such as tons of steel, normalized heat treatment hours, and annealed heat treatment hours. Next, we formulate the dual problem, whose objective is to maximize the economic value of these same inputs. By solving the dual problem, we find that its optimal value exactly coincides with the optimal value of the primal, confirming the strong duality theorem. The resulting dual variables yield the following information. Y1 equals 0, steel. Despite 100% utilization of available steel capacity, the dual value is 0. This means that increasing steel availability would neither reduce total costs nor increase profits. In other words, steel, although essential, is not a bottleneck in the process. Y2 equals 7,341.77 standardized processing hours. Each additional hour of standardized processing would directly contribute $7,341 to the system's value, as it is currently fully consumed. Thus, expanding capacity, whether with more machinery or shifts, is highly profitable. Y3 equals 456.96, annealing processing hours. Each additional hour of annealing would be equivalent to $456.96 in marginal benefit. Although its impact is less than that of standardized processing, it is still a limiting resource whose expansion would add value. In short, the dual analysis reveals that heat treatments, especially normalizing, are the truly critical points of the plant, while steel, despite being used in its entirety, does not determine the optimal solution. Ejercicio 2, Análisis de Sensibilidad. Exercise 2, Sensitivity Analysis. For the second exercise, we shifted our focus to a line of polyester resins for the naval and automotive industries. The primal model maximizes profits for 3 types of resin, Type 1, Type 2, and Type 3, with the following limiting inputs: diacid alcohol, styrene, and water. The initial solution obtained using solver indicated producing approximately 187.97 units of Type 1 and 939.85 units of Type 3, achieving a total profit of $10,225,563.991. Throughout this sensitivity analysis, we explored 2 broad categories of variations: changes in unit profits and changes in resource availability. 1. Reduction in unit profits. Modification. We reduced the profit of Type 1 resin from $8,900 to $8,800 and of Type 3 resin from $9,000 to $9,000, while maintaining Type 2 resin at $9,000. Result: the plant stops producing Type resin and reallocates its capacity to 375.94 units of Type 2 and 751.88 units of Type 3. Total profit decreases by 0.74% to $10,150,375.94, but the new mix is once again optimal under the adjusted prices. Interpretation: a small decrease in unit prices can completely reorganize the production mix, as previously excluded products, such as Type 2 resin, may become more competitive. 2. Increase in unit profits. Modification. We only increased the profit of Type 3 resin to $9,200, leaving the other resins unchanged. Result: the production mix remains unchanged, 187.97 tons of Type 1 and 939.85 tons of Type 3. But total profit increases by 1.81%, reaching $10,338,345.86. Interpretation: as long as the variations remain within the optimality ranges of the model, an increase in the profitability of a product improves profits without forcing changes in the production strategy. 3. Reduction in water availability. Modification. We reduce the water resource from 200 tons to 129 tons, keeping diacid and styrene at 500 tons each. Result: neither the production mix nor total profit are affected, remaining at $10,225,563.91. Interpretation: water was not a limiting resource as long as its availability was above 127.82 tons. Only below this threshold would it begin to condition the solution. 4. Increase in water availability. Modification. We increase the available water to 274 tons. Result. There is also no change in production or profit, which remains at 10,125,563.391. Interpretation. A non-binding resource, such as water in this case, can be increased without providing additional profit, as there is already sufficient slack. Taken together, these scenarios demonstrate that the plant is robust to small fluctuations in input prices and availability, while also identifying critical thresholds beyond which adjustments to the optimal strategy would be required. ARCCO 3, Post-Optimal Exercise 3, Post-Optimal Analysis. 1. Baseline Model. In the first case, I worked with the original linear programming model. This sought to maximize utility by producing 3 types of alloy steel: Type 1, Type 2, and Type 3. 3 main constraints were established: minimum steel availability and maximum allowable times for normalized heat treatment and annealing. Result: the optimal solution was to produce only Type 2 and Type 3 steel. This is because they provide greater utility within the limits of available resources. Type 1 steel was not included in the solution because, although viable, it is not as profitable as the other 2 types. Number 2. Change to the right-hand side of the constraints. Result: the model is still able to adjust to the new resource values, finding an efficient solution within the new limits. Despite the changes, production remained balanced, ensuring profitability and optimal resource use. 3. Increase in the right-hand side of the constraints. Result: the increase in resources allowed for an expansion in production, maintaining the optimal solution and generating an increase in total utility. 4. Addition of a new constraint. A new constraint was added related to the use of the input zinc, required in different quantities to produce each type of steel. Result: despite the new condition, the optimal solution was not affected. The model had sufficient slack to incorporate this input without changing production quantities. Number 5. Changes affecting optimality. Result: despite the changes, the optimal solution was maintained in most cases, indicating that the model is robust. However, some changes did impact total utility, which is important to consider for future adjustments. 6. Increase in coefficients of the objective function variables. Result: the optimal solution was maintained and total profit increased considerably. This is a profitable situation that does not require changing the production strategy. 7. Addition of a new activity. A new product was added, alloy steel type 4, with a higher profit than the others. Result: the model proposed producing only this new type due to its profitability. However, resource usage was excessive. Thus, although profitable, it is not feasible under current constraints. We can conclude that these 7 cases show that linear programming not only finds an optimal solution, but also reveals how that solution behaves in various scenarios. Whether due to changes in prices, available resources, or the introduction of new products or constraints, the model provides a solid foundation for making informed and strategic decisions. General conclusion. Throughout these 3 exercises, dual analysis, sensitivity analysis, and post-optimality analysis, we have explored different facets of the same linear programming model applied to industrial production. 1. Dual analysis identified the resources that truly limit the plant's efficiency. By assigning an economic value to each input, we can prioritize investments where they have the greatest impact. 2. Sensitivity analysis demonstrated the model's robustness to variations in prices and resources. The optimal solution remains valid within defined thresholds, alerting us to when reoptimization is necessary. 3. Post-optimality analysis completed the picture by simulating diverse changes, resource adjustments, new constraints or activities, and changes in the objective function. This revealed the model's adaptability and the boundaries of its flexibility. Together, these 3 approaches confirm that linear programming not only identifies the best solution under fixed conditions, but also equips us with analytical tools to prioritize investments in the most valuable resources, dual; strategically adjust prices and volumes, sensitivity; anticipate and respond to changes in the operating environment, post-optimal. Thank you for watching this video and joining me on this journey through production optimization with mathematical tools.